Now we will have a calculation of the coefficient of self-diffusion for a dilute gas or diffusivity. And as you can see, this is due to transport of molecules when we have a concentration gradient. Remember that we have N1 labeled molecules per volume, and N1 is a function of Z. So we have a concentration gradient. And if you consider on average 1/6 of the molecules will be moving in the negative Z direction and 1/6 moving in the positive Z direction, we have N1, the concentration of labeled molecules at position Z plus the mean free path L. So once again, this L is our mean free path. That's the last collision we had on average before reaching the Z is equal to a constant plane. And these molecules basically had their last collision at Z plus L, and the molecules coming from below the Z is equal to constant plane had their collisions, the last collision at Z minus L. So that's basically the concentration of the molecules did not change in the distance Z to Z plus L and Z to Z minus L. So that's our assumption, because that's the way the molecules scatter off. We have to consider the concentration being a constant in a certain region in space. And if you look at the Jz, once again, this is our particle flux. This is basically equal to the net number of molecules that are approaching Z is equal to constant plane per area per time. So mean speed per molecule, concentration of molecules that was measured at Z minus L, minus the number of molecules that are going below the Z is equal to constant plane. So this is 1/6 V bar and 1 Z plus L per area. So this is per area per time. And the concentration of labeled molecules N1 at position Z minus L, we can estimate for L small, so L is very small. We have Taylor's expansion, so we first equate L to 0, we have N1Z, and then we take the derivative with respect to Z. So we will have minus del N1 del Z at Z is L is equal to 0 times L minus 0. And then for N1 at Z plus L, we can have around L is equal to 0 N1 Z plus del N1 del Z times the mean free path L. So this is very similar to the calculation we did for viscosity, if you remember. In the case of viscosity, we had the number of molecules per area per unit time approaching the plane as 1/6 NV bar as well. So that was the particle flux. So it's the same thing we're talking about, except that in this case we have the concentration gradient, and there we had the momentum at Z minus L and Z plus L, and we have found that for L is equal to 0 we can use this Taylor's expansion and obtain a similar result. Okay, so let's go back to our calculation. So for the particle flux Jz, we have 1 over 6 V bar and 1 Z minus L minus and 1 at Z plus L, and this is approximately 1 over 6 V bar and 1 of Z minus del N1 del Z times the mean free path minus N1 of Z minus del N1 del Z times the mean free path. So we have the cancellation of N1 at Z, and we obtain for the particle flux 1 over 6 V bar minus 2 del N1 del Z times L, and this is basically minus 1 over third V bar L multiplied by del N1 del Z. So this tells us that the coefficient of self-diffusion is can be estimated to be 1 over third V bar mean speed per particle times L, the mean free path. Now we can substitute for L the mean free path 1 over square root 2 the number density n, the total number of particles per volume times sigma. So we will find that the coefficient of self-diffusion will be 1 over 3 square root 2 V bar over n sigma. So we have substituted for L in this equation 1 over 3 V bar L. And we can use the mean pressure of the gas is equal to number density times Boltzmann constant times temperature, ideal gas law, which gives us for n P bar divided by kT. So we find that the coefficient of self-diffusion is 1 over 3 square root 2 V bar over total scattering cross-section sigma times kT divided by P bar. So for V bar, we can use the same approximation we used for the coefficient of viscosity. We can estimate this to be square root 3 kT over m. Remember, this comes from 1 over 2 mv square bar is 3 over 2 kT, equipartition theorem, and v square bar is approximately v bar square. So we find that v bar is square root 3 kT over m. In fact, we found that if we do this properly using Maxwell distribution, basically V RMS is square root 3 kT over m. So we're estimating V bar to be equal to V RMS. Okay, so we can go back to our discussion and substitute for V bar square root 3 kT over m. The coefficient of self-diffusion becomes 1 over 3 square root 2 square root 1 over sigma square root 3 kT over m multiplied with kT divided by the mean pressure. So this gives us for diffusivity 1 over square root 6 1 over P bar sigma square root kT cube divided by m. So I take the kT inside the square root. So basically this is going to tell me about the dependence of the coefficient of self-diffusion on other parameters of the system. So for example, we can observe that at a fixed temperature, you can see that the coefficient of self-diffusion, because we will have P bar is equal to nkt, P bar is proportional to n, so you will see that the coefficient of self-diffusion will be proportional to 1 over P bar and also proportional to 1 over n. And if we have a fixed pressure, at a fixed pressure, we find that this time D will be proportional to T to the power 3 over 2, assuming that molecules scatter like hard spheres, as in our total scattering cross-section calculation. Once again, this is an approximation. As we have seen, this is actually not the case, so there is a small correction. The total scattering cross-section actually has a temperature dependence, so you can see that in our viscosity calculation we have taken into account sigma decrease with increasing temperature, so that instead of having T to 1/2 dependence, we found T to the 0.7 dependence for coefficient of viscosity. Alright, so here if you just assume it's a constant, it's a small correction, then it's approximately T to the power 3 over 2. If you take the sigma decrease as a function of temperature, so you would have maybe instead of 1.5, 1.7 power. Now for the nitrogen gas, let's look at a typical value of the coefficient of self-diffusion. So if I look at 1 over 3 V bar L, this is 1 over 3. For V bar I have found 5 times 10 to 4, for L 3 times 10 to minus 5. So this is the same calculation I did for viscosity, where I have found, you can see here, I have used these parameters. So I have found that 5 times 10 to 4 meters per second is the mean speed, and 3 times 10 to minus 5 centimeters per second, 3 times 10 to minus 5 centimeters was the mean free path. So if you go back to our mean free path discussion, also you can see this L is of the order of 10 to minus 5 centimeters. This was calculated for helium. Okay, so we're taking these typical values for nitrogen now, and we can use these values to estimate the coefficient of self-diffusion, and this is going to give us approximately 0.5 centimeters square per second. So that's a typical value. So if you calculate the ratio of diffusivity to the coefficient of viscosity, 1 over 3 V bar L was diffusivity, and if you remember, coefficient of viscosity, it was 1 over 3 nm V bar L. So these V bar L's will disappear, 1 over 3's will disappear. The ratio of coefficient of self-diffusion to the coefficient of viscosity is 1 over nm. What is 1 over nm? 1 over number of particles, mass of one particle divided by the volume. This is actually 1 over the total mass divided by the volume, which is 1 over the density. So the ratio of diffusivity to coefficient of viscosity is 1 over density. So d times rho over n or nu, the coefficient of viscosity, should be of the order of 1. Now we find that experimentally it is 1.3 to 1.5, and that basically comes from the approximations we're using here. We're going to have a small discrepancy for the ratio of diffusivity to the coefficient of viscosity. So we can see experimentally 1.3 to 1.5, and as I said, it's due to our approximations. Okay, so now I want to use elementary kinetic theory to calculate the coefficient of self-diffusion. This is very similar to the calculation I did for coefficient of viscosity, where I had transport of momentum. Here we have transport of molecules, and we can see that the net particle flux through z is equal to constant plane is 1 over 6 v bar n1 at z minus l minus 1 over 6 v bar n1 at z plus l. So mean free path is L, and so when we are at a distance L from the z is equal to constant plane, we had the last change in the concentration due to scattering of molecules. Okay, so since the mean free path is a small number, we can estimate these concentrations using Taylor's expansion. So this is Taylor series, and you can see that if we do so, we find that the coefficient of self-diffusion is 1 over 3 v bar L, the mean speed per particle times the mean free path. And we substitute for the mean free path 1 over square root 2 number density, total scattering cross section, and sigma, and we can substitute for n p bar over kT using ideal gas law. So this is assuming it's an ideal gas. And therefore, we can find for the diffusivity, if we also use our approximation, v square bar is approximately v bar squared, and v bar is square root 3 kT over m. So in Maxwell distribution, we're basically saying v bar is similar to v RMS, so it's very close. So we can use this approximation. And so for diffusivity, we find 1 over square root 6, 1 over p bar sigma square root kT cube over m. At a fixed temperature, p bar is proportional to n, and we have p bar appearing in the denominator. So diffusivity is going to decrease with increasing number of molecules per volume, increasing pressure at a fixed temperature. At a fixed pressure, we find that diffusivity increases with T to the power 3 over 2. That's neglecting temperature dependence of total scattering cross section. And for nitrogen gas, if you substitute 1 over 3 V bar L, typical values, we find a typical value of diffusivity is 0.5 centimeters square per second. And the ratio of diffusivity to coefficient of viscosity is 1 over the density, and d rho over eta should be of the order of 1, but we find that experimentally it's 1.3 to 1.5, which is due to the approximations that is involved in this calculation.